Yeah, thank you for the introduction, and thanks for everybody staying so late until the last talk. I'm going to be talking about Go and graphs. And actually, the About Me page is somehow relevant for this talk. So I'm VP of Product at Dgraph Labs, which is a distributed graph database written in Go. Before that, I was working at a company doing source code analysis that we used to use a graph database to store the code. And before that, I was at the Go team. So I've been doing Go and graphs for quite a while. So I decided to give a talk about how to put all of that stuff together. So the agenda is going to be, we're going to know what graphs are, then we're going to see a graph database in Go, then graphs in Go, and then graphs in Go in a graph database in Go. And then we're just going to keep it from there. So we are hiring. If you're interested, we're hiring around the world, but mainly in San Francisco. So let's talk about graphs. I'm sure that all of you have used graphs in the past. Like, how many of you use graphs in general in their tech world? OK. Those that have not raised your hands, you still do it, even though you know it. Because graphs are everywhere, right? Like, for instance, this is an example of a pretty straightforward graph. Let me check if I started my timing. No, I did not. Great. So this is a movie graph, and it represents we have nodes and edges. This is what graphs are made of, right? So you have Steven Spielberg directed Jaws. Jaws is a comedy, apparently, and also thriller, and Jurassic Park is also a thriller. So you have all of these different relationships between concepts that we call nodes, and then the relationship across concepts, we call them edges or predicates, or there's a bunch of different ways of calling them, right? There's actually a little bit more. There's also what we call properties, right? And properties are something that you attach to a node, but it doesn't necessarily attach to some other node, right? Some databases make the difference, and this is what they call the property graph, I think. It's called property relationship graph or something like that. It's some way of calling it. It's really not that important. The important thing is we have nodes and things attached to them. Some of them are values, properties, like this movie was recorded in 1975. Some others are actually linked to some other entities, like this movie was recorded by Steven Spielberg. Cool, so now that we all know what a graph is, let's think about how do you store them in a database. And this is kind of interesting, right? Because I'm sure all of you have used relational databases. So the first reaction is I'm going to use the relational databases I know how to use. So you look at this, and you're like, OK, so let's think about how to store not the whole thing, because it would be quite complicated, actually, but just movies and directors, OK? So just a movie is a director directs movies, and movies are directed by directors. So there's this thing that I'm sure you've all learned. If it's one-to-one, you can use foreign keys. If it's one-to-many, then you need to use a foreign key on the side that is one, unless you want to do it on the other direction, and then you need to create a list. And then if it's many-to-many, then you need to create a table in between. And all of this, you need to make the decision now, right? As soon as you start thinking about how to write the program, you need to make these decisions and stick to them. Cool. So, a movie has a director. So I'm going to create these two tables, movie and director, and say that, for instance, Jurassic Park, the movie was directed by director. Now, if you want to go the other way around, you're going to need to define an index. But that's OK. That's not super hard. It's doable. Cool. So you start doing this, write your whole thing. You use, of course, cascade model. So it takes a couple months of writing code, and then you test it, and then maybe it works. And then eventually, you deploy it to production, and you get your customers. And then you discover that some movies have multiple directors. Yay. So at this point, what you need to do is rewrite all of your code, and also create a movie director. What is a movie director? Nobody really knows, but it's there, right? Like, it's something that you need to create just because you want to store that graph inside of a relational database. And the whole problem is that relational databases are great except for relations, right? Like, they're great for tables, and they're super efficient. But for relations, and especially complex relationships that change over time, they're actually not that good. OK. So relational databases, not great. NoSQL, right? Like, everybody uses NoSQL. That's the solution to all of our problems. So how about no relational databases? Well, it is actually somehow complicated, because what you're going to need to decide at this point is not necessarily how you model it, but where do you put the data, right? So let's go, like this is an option, right? You could say, oh, the director is gonna have a list of all of the keys of the movies they directed, and then you have a single document per movie that they directed. Now, if I want to get Steven Spielberg and the names of all of the movies, I need to do one query to get Steven Spielberg, and then n queries for every single one of the movies. And this is not fast, right? So this is not great. Easier, boom, done, fixed, right? Now it's only one query. Now, what happens if a movie has multiple directors? You cannot do that anymore. So this is not always great. So the solution, obviously, is repeating your data. Now, if you do this, you solve both problems. Now, you're going to be able to have both directions and performance. But at this point, now you're repeating data, and eventually you'll forget to update one of those. And at that point, if you don't have consistency, what's the point of having a graph database? You could just store this in JSON, right? So that is the problem. It's like there's a lot of decisions that you need to make early on that are going to force you to go one way or the other without really knowing whether that's the right way. So, graph databases. Let's talk about graph databases real quick. So, the idea of a graph database is that the way you model, so if you remember, let's go back to here. This is your graph database model because you model things as graphs, right? So when you wrote that arrow directed from Steven Spielberg to Jaws, you didn't have to think about any kind of implementation. You just wrote it because they're related. And that's what you do in graph databases. What you do is you store facts, we call them. And a fact is something that says something about something. So if you think about, let's go back to here. If you have a thing about the fact that that movie is called Jaws, what you're going to store is you're going to say Jaws was recorded in the year 1975. That's one way of doing it. Or Jaws was directed by Steven Spielberg. You're not thinking about all of the other possibilities. You're just thinking about these facts right now. This is actually false because you don't really store Jaws as the identifier or anything like that. What you're going to be doing is actually you're going to be storing some UID, we call it, universal identifiers. So 0x1 has name Jaws. Also 0x1 was recorded in 1975. Also 0x1 was recorded by 0x2, and 0x2 has name Steven Spielberg. Right? So this is the data that you're actually going to be storing in a graph database. There are no tables. The only thing that you store are these things. And if we go a little bit more into detail, 0x1, 0x2, those are UIDs, universal identifiers. Has name, was recorded in the year, and all of those things. We call them predicates. And it's interesting because predicates are both properties and edges. We don't really care, right? So the fact that something points to a string, the name of the person, or points to another node, the director, right? It doesn't really matter. It's going to store the same way. And then Jaws and Steven Spielberg and all these values, all these strings and integers are values. So what we do is we store all of that in a key value store. And that's it. So the key value store is going to store the key, is going to be the UID, and the predicate name. And then the values are going to be all of the values attached to that. So in here, for instance, 0x1 has name Jaws, or 0x2 has name Steven Spielberg. If something, for instance, if 0x1 was directed by many people, you would actually have multiple values there. You would have 0x1 was directed by 0x2 and 0x3 and 0x4. And you would have all of those together in the same place. This means that when you're fetching data, we're actually going to be able to fetch everything in just one single query, and then just iterate really fast. So let's go through life of a query. And if anyone has ever worked at Google, this is the first presentation you learn. It's life of a query. How does it work? So we're going to do the same thing. So first you need to find where do you want to start from. 0x1, Steven Spielberg. Then you're going to append to that 0x1, to that UID, whatever predicate you want to traverse. So once you have that, you're going to get a bunch of values. And then from those values, you're going to get, which are UIDs, you're going to get the next predicate that you want to traverse and continue and keep going, right? So basically it's UID, predicate to UIDs, UIDs, predicates to more UIDs, and eventually you get some values, strings or whatever you're looking for. So the good thing is that whatever you're doing, there's no values other than in 64s, right? So all of the keys are integers, which means that when you're trying to do things like compression or union of lists or intersections, all of those things, it's actually really easy. There's no strings or anything else to be taken into account, so it makes it much easier and much more efficient. So an example, right? Like 0x1234. Let's say that's me. So I want to find all of the friends of 0x1234 and then find their names. Okay? So I'm going to start 0x1234, attach is friends with, and I'm going to get the values, 0x ABCD and BCDE. And then from there, now I have those two, and I'm going to get two more names, Diggy and Augie. Bonus points for anyone that gets the reference to Augie. And that's what we're going to be returning. Okay, so that's how queries work. Now, given the time, yes, I'm going to pass that. So, yeah, I don't have time. We could talk about the fact that you don't always know what is the first UID, so you need to figure out how to find those, and we do that with indexes. But we don't have time, so whatever. OK, so how is this related to Go? Other than, it's written in Go. So let's think about what Go is, right? Like Go, let's go, like it is a closing keynote, so let's go closing keynote-y, right? Like Go is a community, and Go is an open source language, very active and all that stuff. But at the end, Go is a bunch of zeros and ones, right? That's what you store. And that's what we're going to look into. I want to think about what is Go, like a Go file, what does it contain, and how can we understand it? How can we analyze it? So let's say that you have this, hello Gophers, right? So this is this. Is actually, there's a mistake, find it. So there's a bunch of bytes, right? And this, if you send it to the compiler is going to see this thing, not really that other thing. That's what we read, right? But if you think about that, right, like this is not very useful. So we're going to think about a better way to understand that, which is actually somehow how we read it, which is it's a list of tokens. So you have package. You don't read it as P-A-C-K. You just read the word package. And then main, you read it as the word main, et cetera, right? So you have a bunch of tokens, and they're in a sequence. And this starts to be a little bit more how people understand code. But this is actually not even how you think about it. Because when you talk about things, right, you're not going to be talking about, oh, the token main. You're going to probably be talking about the function main and everything that has inside, right? So there's actually a little bit more of a structure to it. And that's what we call an abstract syntax tree, right? So an abstract syntax tree, what you're doing is getting those tokens and structuring them in a way that makes sense to the program, creating units that are somehow semantically significant, right? So functions or type definitions or expressions, whatever it is, all of those are trees. And trees are somehow graphs, right? But the thing is that as soon as you get this and you start adding anything, now you have graphs. So for instance, what could we add? Well, if you think about using VS Code, for instance, for this, when you command click or whatever click on println, you're going to go to a different part of the code, right? So that's a relationship. There's like, oh, this is defined there, right? But there's many more. Like the type of something is also a relationship. Or in the file, also the file is a relationship. Or in package, a relationship. All of these things create relationships. And as soon as you start adding those to this syntactic tree, you end up having a graph. So, yeah, yo, Doug, I heard you like Go programs, so I wrote a Go program to store Go programs in a Go program. So now let's see one of those. Let's think about the most basic graph, which is the graph of importing, right? When a package imports something else. Just that, not looking into anything else inside, just looking at that. The main pieces of this program actually are that package. If you've never used it, if you need to parse Go, that is the best package I know. It's super simple. I'll show you the code in a minute. It looks super easy, and it works really well, like 99% of the time. I'll show you in a place where it breaks, and you can take it as a issue. Yeah. And also, I'm using Dgraph, so I'm using Dgo, which is the Go client for Dgraph. So we're going to create a schema, and we're going to have predicates, right? So these predicates are going to be two kinds. We're going to have ID, which is the import path, right? So a package has an import path. And then a package also imports a bunch of other packages. So for example, main imports thumped. It's going to be A is called main, and B is called thumped, and A imports B, right? And that is literally what we're going to be sending. That is what a mutation is in Dgraph. This is the information you're going to be sending and what you're going to be storing. So let's do some demo time. So let's see the code real quick. So the part that I really like is, in order to parse the code, it's literally just these lines here. That is everything you need to do to parse the code, which is super cool. Compared to if you had to use Go AST, Go, all of those things, this is super powerful and works really well. And the important thing is I'm here saying the mode. So I'm saying I need to parse only imports, right? If you wanted to parse deeper things, then you need to go and add more modes to that. And then what I'm going to do is I'm going to connect to the graph database. I'm going to set the schema. And then for every package, I'm going to be sending mutations. And this looks kind of complicated, but what I'm saying is that, oh, the ID for this package is the ID that I parsed. And then the type is package. And then for every single one of the imports, I'm going to say, here, I'm going to say this package imports that UID, that other package, and that package has that name, right? So that's everything I'm doing. It's just sending mutations one after the other. So let's try. So let me run, 9080 because it's gRPC, and 8080 for REST, and Dgraph standalone master. Cool. So now this is running. And now I'm going to analyze. I want to go even more meta. So I'm going to analyze the source code for the graph database reading Go with a program reading Go to store in the graph database in Go and all that stuff. So I'm going to run imports. And this is going to parse all of the code in there. It's going to start sending. Those are mutations that we're sending, right? So those are the changes that we're sending to the database. And now I should be able to connect to HTTP, localhost 8080, and start querying things. For instance, I'm going to say, this is very similar to GraphQL, but it's not. We also have GraphQL, pure GraphQL, but I'm not going to use it today. So type package, give me the IDs. So now you have a bunch of IDs in there. And you can also get the JSON, so you can see the names of all those packages. The interesting part is that you can also say, actually, I'm going to use name. So it shows it on the graph directly. I think it's a little bit cooler. And then I'm going to say, also give me all of the imports, and also give me the IDs of those. And now you're going to start to see like all of this mess, which is Dgraph itself, right? The interesting thing about this is that it is somehow hard to see, but as soon as you see this, the first thing I saw was, what is this? Like, that is weird. It's actually, interestingly, it's the tokenizer. And the tokenizer, what it does is it creates indices. And we have an index that does full text search that is actually based on a different open source project that is written Go, which is, I don't know how to pronounce it. I think it's Blev, whatever. It's a great project that we use, but I don't know how to pronounce. So the idea is that thanks to this, you're able to find like also some packages that are never imported or do not import anyone. We can also add, so when you add a tilde, what you're saying is go back. So what are the packages that import this? So you can do that and find more information. But still, like, even if you do that, that looks even cooler now. You will see that there are some packages that are never imported. And that's actually because the tool is actually failing to parse some things. And even worse than that, there's one repository that I was not able to parse with this tool, which is, golang.org, x go. And if you do imports, it fails with an error saying, cannot find Go modules. Go modules, yay, off. And now it fails with a different way saying, Go list gives conflicting information. I don't know what that means. So yeah, I was not able to parse Go itself, which is what I wanted to do originally because of this. So yeah, the import path, which, by the way, this slide was here just in case the demo didn't work. But this is exactly what you would see, which is what you saw, so that's great. And now I wanted to do a different program. So it is to control flow graph. How many of you have heard about control flow graphs? Okay, so a control flow graph is actually a very interesting way of visualizing a program because instead of talking about what the code actually looks like, it talks about what going over the code would look like for you, right? Like basically it's like when you start the main function, for sure you're going to go into if greeting. But then you might go to print hello or print bye, and you still don't know, right? So you have two different options, and that's the idea. You go to either print hello or go bye, but then at the end you go back to the same route, printing gophers. Right? So this would print either hello gophers or bye gophers. We still don't know, but the idea is that you're able to represent this. Now, doing this is really hard. Like generating a control flow graphs with Go, it's super hard, so I did not do it. Instead, I use a package that already does it for me. It's actually built by Alan Donovan, which is the guy that was also behind Guru, which used to be called Oracle, that tool that you might have heard about. So it does really interesting analysis of code, right? The interesting thing is that that is a package that you can import. So what I did was I got that, let's see here. And so what you need to do to parse CFG is you need to parse all of the files with the parser, which is Go parser from the standard library. And then, where was this? Oh, there you go. So config.new, sorry, not config, CFG, control flow graph.new. That is the line that parses a given parsed file and generates the control flow graphs. And it's going to give you a list of blocks. So what I'm going to do is go block by block, and for every block, I'm just going to say, this block contains these instructions. Also, after this block, you could go to this block or this block, right? So it's super simple code. It looks hard because it uses protocol buffers, to be honest. If it was not protocol buffers, this would be much simpler, I think. But at the end, so what we're able to generate is we got all of these blocks, and then we just send them mutate, and we're done. So let's run that. I'm going to do it hello world.go. So I'm going to do it first with a very simple program, right? So no. OK, so it's going to be CFG hello world.go. And then if we go here, I should be able to do q func type block, block name. There is a block. And then it has nodes, and those have bodies. And we can also try to display them there. So a block, there's only one block, because the only thing you can do is print something, and there's no alternative, so that's everything you can do. And you print done, and then you're done, you return. Okay? So that is the simplest one. So now let's go with one that is a little bit more complicated. Hello.go. So this one, there's a for loop, and inside of the for loop, we're going to be printing something, and then there's going to be an if statement. So it's kind of like FizzBuzz, I think it's called, that program that people need to write when they're learning programming. So basically the same thing, but a little bit simpler. So let's analyze that one, but before I do that, let me drop the database real quick, because otherwise I'm going to mix both runs. OK, so CFG hello.go. Okay. And now we're going to run the same query. And now you're going to see that this didn't work because look at that. We have block 4, block 5. Like blocks are not really connected. So it's because we need to actually also connect them. So we're going to connect them now. And now you can see block 0 that starts declaring a variable. So you can actually see the code in there. And then goes to block 3, that is the for loop. And then it goes either to the block 2, which is once you're done with the for loop, or you could go to the if done, which is after the if, because the if didn't work, or you could go into the for body, which is the first one. So basically, actually, no, you could go to this one, so this one can go back to up. So you're going to get like these loops. The interesting thing is that you will be able to, from here, start doing interesting analysis, because you could find things like, find all of the places where I'm using println, and figure out how are they looped inside and how many times I might execute something like this. So you can start to do a little bit of interesting analysis that otherwise would be also doable, but I think that with this, you're going to be able to get it a little bit easier. So schema, demo time, it worked. So, the kind of ideas that I'm thinking about building with this is I would like to try to have GoDoc instance. So if you go to godoc.org, there's a lot of analysis like, oh, this type satisfies that interface, or this interface is satisfied by all of these types, or these are the functions that are called inside of this function, or there's a lot of different things that I think would be really useful, and exposing something like that would be really useful for people that are trying to better understand the language at a higher view. I've done some analysis with BigQuery, which were really useful, but the problem with that is that then you need to do analysis based on text, right? And in here, we actually are able to extract way more information and to find relationships that otherwise were really hard. Also, it'd be really interesting to, there's a lot of different graphs analysis. Like I only showed 2, but there's easily tens and more than that. So if you were able to merge all of those together, that'd be really interesting. I think that, no, at least I have not seen anyone actually doing that and putting all of these different analyses together and trying to figure out whether we can learn something new. So types graph is one of those graphs. And then the last thing is basically, what if we could use, like right now, in order to do source code analysis, you need to first parse all of the code. And very often, that's actually super long. That is actually a very costly process. So if you're able to expose all of the graph already parsed, then some researchers could do something interesting with that. So if you want to check it out, bit.ly, that bit.ly link is at the slides, and also all of the code. There's one more that I could not demo, is under code as graphs under my GitHub. I'm also on Twitter, I have an email, and we're hiring.